Elon Musk didn't build companies. He built engineering systems. And once you understand the system, you realize it can be copied. Engineering beats genius. Most companies fail not because of lack of ideas, but because of bad engineering decisions. Elon Musk approaches problems like a chief engineer, not a CEO. This mindset is why Tesla, SpaceX, and others scale faster than traditional companies. But underneath the persona lies a machine of logic and process. It treats business challenges not as market problems solved by branding, but as engineering problems solved with physics, math, and proof. The first layer of Musk's system is first principles thinking. This isn't a new concept. It's a physics-based approach to problem solving that dates back to Aristotle. Instead of reasoning by analogy, which is what most people do most of the time, you boil things down to the most fundamental truths you can imagine and then reason up from there. It's about deconstructing a problem into its core components, the absolute, undeniable truths, and rebuilding your understanding from the ground up. In this framework, every complex problem is broken down to its physical and economic fundamentals. You don't just accept the current price or method as a given. You ask, what is this thing actually made of? And what is the spot market price of those constituent materials? This forces a complete reevaluation, free from the baggage of how things have been done before. At SpaceX, this was the key that unlocked the economics of spaceflight. When Musk first investigated the cost of buying a rocket, he was quoted prices as high as $65 million. Instead of negotiating, he asked a different question. Rockets were redesigned from raw materials, not from expensive, pre-existing supplier catalogs. The analysis was startling. The raw materials, aerospace-grade aluminum alloys, titanium, copper, and carbon fiber, were only about 2% of a rocket's typical final price. The vast majority of the cost was not in the stuff itself. The high price wasn't a law of physics. It was the result of accumulated legacy processes, Byzantine supply chains with multiple layers of markups, and a lack of incentive to innovate on cost within the established aerospace industry. It was a tax on inefficiency. Armed with this insight, SpaceX's strategy became clear. They designed rockets to be made as simply and cheaply as possible, using common materials and standard manufacturing techniques wherever feasible, rather than relying on exotic, sole-sourced components. The process is methodical. First, question every assumption. Why is this part designed this way? Why does this process exist? Then do the basic math yourself. Calculate the theoretical minimums for cost, weight, and energy based on the laws of physics. You must ask, what must be true for this to work? What are the fundamental physical laws governing this system? This grounds the entire effort in reality, not opinion. Then, you must ask, what is merely convention we've accepted? Strip away reasoning by analogy and tradition. The phrase, "we've always done it this way," is a red flag, signaling an opportunity for innovation. By rebuilding from this clean foundation, first principles thinking reveals solutions hidden in plain sight. It's a methodical process, not magic, that cuts costs dramatically and makes the impossible possible. The conventional wisdom in modern manufacturing is to outsource complexity. On paper, this strategy appears efficient, allowing a company to focus on its core competency while leveraging a global network of specialized suppliers. But this neat diagram of distributed work often conceals a messy reality, a web of hidden delays, constant communication overhead, and the friction of conflicting priorities. Every external partner introduces another potential point of failure and another layer of management. When you outsource, you are fundamentally bound to a supplier's schedule, their non-negotiable cost structure, and their own appetite for innovation, which may not match yours. A critical component might take a supplier 6 months to deliver, but an in-house team could potentially turn it around in 6 weeks. You're not just buying a part, You're inheriting their limitations, their profit margins, and their entire operational cadence. Musk's approach is the direct opposite, a philosophy of radical vertical integration. At Tesla, this isn't just about assembling cars. The company builds its own batteries, develops its own software from the ground up, designs its own custom AI chips, and even engineers the robotic tools that build the factory itself. This pattern repeats at SpaceX, where the most critical and performance-defining components are kept in-house. The company produces its own rocket engines, the complex avionics that guide them, and the advanced composite structures that form the vehicle's body. This strategy of owning the stack systematically reduces external dependencies, which dramatically accelerates iteration cycles and grants the organization complete system-level control. Problems that would take months to resolve through a chain of suppliers can be solved in days. Proximity is a powerful catalyst. When the battery team, the software team, and the manufacturing tooling team share the same building, information flows at the speed of conversation. A design change can be proposed, validated, and integrated into the production line almost immediately without purchase orders or contract negotiations. Owning the full technology stack empowers engineers to make holistic trade-offs. They can decide to accept a minor compromise in hardware if it unlocks a major gain in software performance, or adjust a manufacturing process to enable a more elegant product design. The goal is no longer to optimize a single component, but to achieve a better overall system result. This path is not easy. It requires immense upfront capital investment and a staggering breadth of expertise across multiple domains. But the long-term dividends are clear. Fewer external risks, a sustainable pace of rapid innovation, and more cohesive, tightly integrated products. The principle is simple. Take on more work and complexity now to gain crucial speed and absolute control later. It's a strategic investment in your own team's capability. Ultimately, vertical integration is about tightening the feedback loops between every stage of creation. This is the true heartbeat of any fast-moving engineering organization. The ability to design, build, test, and retool your own processes without waiting on external contracts or shipping schedules is what allows the system to build and maintain unstoppable momentum. In traditional engineering, failure is avoided. Long design cycles, endless reviews, extensive pre-launch simulations. Perfection first minimizes risk and dramatically slows learning. In Musk's system, failure is data. SpaceX launches, explodes, analyzes, and rebuilds faster than competitors can schedule meetings. To outsiders, it looked like failure. To engineers, each failure was rich data. Unknown failure modes become known and fixable. The rate of learning is proportional to the rate of iteration. Tesla continuously changes production lines, introduce new tooling, test a different robotic process, reconfigure to shave seconds. It's not recklessness, it's efficient learning. A failed rapid test often costs far less than a multi-year flawed program. More learning cycles per year compound knowledge exponentially. Speed becomes a strategic weapon. The organization that learns fastest wins. In the fourth system, decisions are not driven by the subjective desires of marketing or the quarterly targets of finance. Instead, they are fundamentally rooted in the objective realities of engineering constraints. This isn't to say other departments have no input, but their requests are framed by what is physically and economically possible, not the other way around. The process begins and ends with the engineers who are closest to the product and its underlying physics. When this principle is ignored, teams are inevitably asked to defy the laws of physics or economics to meet arbitrary targets. A marketing team might demand a product that is simultaneously lighter, faster, and cheaper without understanding the inherent trade-offs. This creates immense friction, slows progress to a crawl, and almost always results in compromised, underperforming products that fail to satisfy anyone. The organization wastes energy on internal battles instead of solving external problems. In a truly engineering-led organization, the traditional corporate hierarchy is inverted. It's not the highest-paid person's opinion that carries the most weight. Here, physics is the ultimate arbiter. The universe doesn't care about a CEO's vision or a marketing slogan. If the math, backed by rigorous analysis, says an idea won't work, the idea dies on the spot, regardless of its perceived marketing appeal or how much leadership wants it to be true. Design reviews are not about opinions or aesthetics. They are intense, data-driven examinations of simulations, prototypes, and first principles analysis. Every claim must be supported by evidence. For example, an engineer might present a clear, quantifiable trade-off. We can achieve 10% more performance, but it will require a material change that increases unit cost by 50%. Or, we can accept a 5% performance penalty by redesigning a component, which in turn cuts its cost by 30%. The team then chooses the latter, because analysis shows the 30% cost reduction allows for wider market adoption, and the 5% performance dip is imperceptible to 99% of users. The decision is logical, defensible, and aligned with the project's core objectives. This data-centric approach aligns the entire organization around testable, objective goals. Subjective arguments are resolved efficiently by running the numbers, building a quick prototype, or conducting a definitive experiment. The data ends the debate. This clarity accelerates everything. Precious resources, time, money, and talent are focused on solving real, tangible problems, not navigating internal politics or chasing unachievable goals. The result is a faster path to a better product. This approach is spreading. Defense technology, artificial intelligence, energy infrastructure. In capital-intensive, hardware-driven fields, slow, outsourced development is no longer competitive. Control your tech stack and iterate quickly. It becomes a decisive advantage and a competitive moat. New defense companies build hardware, test in the field, and iterate based on user feedback, shrinking timelines from years to months. AI leaders design custom chips, build massive data centers, and write the full software stack to maximize performance and efficiency. Energy players integrate generation, storage, and grid management to deliver reliable, intelligent solutions. The lesson: when building complex, integrated systems, design, build, and test with speed and control, the engineering-first model shows how. First principles, vertical integration, rapid iteration, and engineering-led decisions are interlocking components of a single system. Together, they create a self-reinforcing cycle of innovation. First principles define the goal. Vertical integration provides control to pursue it. Rapid iteration provides the learning to achieve it. Engineering-led decisions guide with objective reality. Each test generates data fed back into decisions, completing the loop and accelerating progress. This integrated system, working in unison, transforms an organization into a relentless learning machine. Elon Musk is not the system. The enduring legacy is not the personality. It is the process. A commitment to first principles, strategic vertical integration, a relentless pace of iteration, and engineering-led decision-making. These practices combined create a repeatable method for solving hard problems in the physical world. This system can be learned. Break problems into fundamental truths. Bring critical processes in-house. Embrace small, fast failures. Empower technical experts to decide with data and physics. Adopting this system requires cultural change and long-term investment, but the rewards are immense. Engineering discipline, fast iteration, and brutal focus on fundamentals. Systems scale. Personalities don't.